Welcome. This is Thorsten Steinbach, working for IBM for the IBM Cloud as an architect, where I'm actually leading the Cloud Data Services efforts around Cloud Data Lake. And I'm accompanied today by Paula Tashma, who will basically lead you through the second part of our session today. And she's also working for IBM Research, and has contributed a lot to the capabilities that we have built into this data lake platform that we're going to show you today. I'm going to start first to walk you a little bit through our take on a cloud data lake that we have at IBM and how we actually architect our data lakes, especially our reliance on Spark and how we do that and make it actually serverless. That will be the first part of that. And in the second part, actually, we are going to walk you through a specific implementation, a real implementation that actually we have implemented and went into production with for serving large volumes of weather data on demand. And part of that is a major contribution that we have added to Spark for indexing, which we are also proud to announce today here in the session at the end of the session. We're going to announce the open sourcing of this indexing technology. Okay, so let's start with our definition and implementation of data lakes in the cloud. So first, a conceptual overview, what we consider data lakes or cloud data lake. The cloud data lake is actually an on-ramp of analytics, of big data to analytics. And this can be data that either is already somewhere stored and basically you need to get it into your data lake through ETL processes, or you basically use a continuous ingest from telemetry data, click streams, IoT data, log data, and so on into your data lake. And the data lake then is going to provide you all of this tool chain starting from very raw data that you first need to explore and understand in first schema and so on, and then slowly you make your way up to prepare it, enrich it, but also optimize it on disk, which is very important for a cloud data lake with disaggregated storage, because then optimization of the layout, the format, partitioning is critical for performance of your analytics. And we also consider a data warehouse still to play a role here attached to a data lake for certain specific use cases where you have very high demands on response time SLAs. So that's why we also consider it critical that you have capabilities to also transport and promote data, hot data, certain parts of the data into a real data warehouse for those use cases. But that's something that's actually changing. I'm going to touch a little bit also towards the end of my part. One of the specialties that we actually focus on when we build data lakes and define our platform is that we actually focus a lot on serverlessness of that one. So that means you're basically, as a consumer, as a developer, as a user, you're not actually involved in resource management in terms of hosts and things like that. It's auto-provisioned, auto-scaled on demand based on your actual workload. And also the billing of that is completely basically based entirely on the real workload run. And what comes with it also is a high availability out of the box for everything you do. So you don't have to provision multiple instances of this data lake or something like that. We actually have three major components in the foundation that we use for our services to make a serverless data lake. It's a serverless storage, which is actually object storage. So we at IBM Cloud also have an S3 compatible cloud object storage. Serverless runtimes, where we also have several layers. We have function as a service, we call it Cloud Function. We have container as a service on demand, which is Code Engine in our cloud. And then we have a serverless analytics, which is a service that I'm going to show you next. That is a core of our cloud data lake, which is called SQL Query. And what that service is in fact a serverless Spark service. So the architecture of the service, basically the rough architecture looks like this. It's actually really community Spark that we are running here, but we run basically this in a big farm of Spark clusters that we provision. And not just Spark clusters, even Spark applications, Spark contexts are actually kept around in a basically pooling mechanism. So whenever a workload comes in, we can immediately serve that. And we have then the sandboxing within this entire environment using the SQL grammar as a sandbox, basically. So with that, you can run anything on demand that Spark SQL can do. The entire Spark SQL syntax is supported, Community Spark, and we have added a couple of capabilities here to make this more complete in terms of the value proposition that you can do. Like we've integrated a Hive Metastore out of the box, fully managed as part of this service. So you can do all the data management. We have implemented a sophisticated data skipping indexing feature. That's what we're going to take a look at later today. And we also have some functional capabilities like time series SQL extensions and geospatial SQL extensions, where just the SQL language itself is extended to have native operations on time series data or on location data. All of that on our data and cloud, which is kind of object storage. We also have attached basically as a source or as a target relational databases like our own DB2 in our cloud. And event streams is a Kafka as a service. And I'm going to talk about that also towards the end a little bit, what we're going to do here. The capabilities that this enables can be grouped in these four major boxes that you can see here. So it starts with data ingestion that the service supports into basically landing data into the data lake, into basically the storage of the data lake, so object storage, transformation of the data. That's obviously a big strength of Spark itself, right, as a framework. So all kind of data transformations, data itself, but also layout, formats, reformatting, repartitioning, all of that. Then the actual analytics, which is really queries, scale out, basically queries, generating reports and things like that. And data management is basically the encompassing thing that goes along with all of those, because that's your metadata management, right? Table definitions, rolling in and out of partitions, and also the index management, frankly, is part of that. So that basically is all exposed in a serverless fashion. I just want to give you a brief idea how that looks like. Our basically key user interface is looking like this. It's a SQL experience where you can just run SQLs, right? So, and all of the capabilities are actually expressed through SQL syntax. So when you go for our samples, you see that. So for the analytics part, so that's all of the OLAP or kind of BI queries that you can do. But it also covers ETL capabilities, like data transformation, like for instance here, a repartitioning into a Hive partition schema on disk, or writing data from a data lake into, let's say, a relational database into DB2. And you can see this is all just SQL syntax that is basically used here to express all that. And same also for data management, like indexing here, or like your catalog management, right? Creating table and partition management of tables. Actually all just SQL. So that's why it's a pretty lean interface, and the SQL syntax is where actually all the functionality is contained. All of that is running Spark behind the scenes, serverless, and we automatically scale it out for you. We can run these farm of Spark servers, and a Spark application, when we basically use it to run a job for you, we also auto-scale that in terms of the number of executors needed, depending on the data volume. It's nothing that basically the user will have to do. That's something that basically where we use the capabilities of Spark in a fashion that the user just can use it out of the box. I want to basically, for the sake of this presentation today, give you some idea of why we're actually here. First of all, we are proud to share, of course, what we are doing here with IBM and that, but actually, we also clearly see where Dremio actually can fit in, right? So by relying on Spark, this is really scaling out very well, especially batch performance is good. It has a lot of flexibility, for instance, also to work with real-time data and things like that. But interactivity is something where I think Dremio shines. So we have started actually to work with the Dremio user interface, or the Dremio stack, and we have deployed it to our cloud. So this is now our Kubernetes service. This is a Kubernetes cluster in the IBM cloud that I've just deployed here with a worker pool. And if I look inside, so this is no standard Kubernetes here, but you can see I've used the Dremio Helm charts to set up here, the standard Dremio Helm chart to set up a Dremio cluster. And then I basically can use Dremio just to work on the same data of our data lakes, right? So this is now really cloud object storage of the IBM cloud, which is S3 compatible. That's why it was easy to connect. And I can just go here and run my queries in a very interactive way. And that's what we find very attractive and would like to explore further as we go along. And like, for instance, we would also like to see to maybe enable our cloud data lake to show up here also as something you can directly import the metadata from, like a data lake itself. But that's something that we're looking into. But I just want to give you some idea of why actually we think Dremio is an interesting community for us actually to basically get connected to. So yeah, so this is what we have and what we have built out, and it's available in our IBM cloud. There's a freemium support, so you can free plan, so you can just sign up for free and just start playing with that. It's actually really approachable. What we're doing this year, I want to give you a little bit of an idea of what our current focus is actually we are elevating real-time data to become the same kind of first-class citizen-like data and object storage, right? And that means actually all of the capabilities that you can do on data at rest and object storage, like running queries against it, doing data transformations, right? ELT type transformations of data and object storage, enriching it and so on, cleansing it. All of that should also be or will be possible to do in data in motion. You can run real-time queries and you can run transformations on the stream, right, from one topic to another one. And obviously, you can also basically cross those boundaries very nicely by just saying, you know what, I'm running a SQL job that lands data from the stream into object storage in a continuous fashion. And for instance, into a certain format, Parquet, partitioning in a certain way, and maybe do some pre-filtering, pre-processing, using the full syntax of SQL. And the underpinning of that will be common metadata, where we bring together Hive metastore with the Kafka schema registry. So to make this metadata also covering both sides in a seamless fashion. So that's something where we're working on, and there are some things that we have very soon available here. So stay tuned. And I want to basically take up this metadata topic because I think that's also another thing that we think is highly important. Actually, for us also to go into this lake house notion that you see nowadays more and more actually being promoted, which, as the name indicates, right, is a data lake that is more warehouse capabilities you can directly do in a data lake. And in our interpretation of that, the key enabler for that is metadata, a more complete metadata, heavy infusion of metadata. So not just schema metadata, but also consistency metadata, asset metadata using these table formats like Delta Lake and Iceberg, data governance. So IBM have a strong portfolio also that we want to pull in here for governance policies that can be enforced then, and indexing. And as indexing is one of the key innovations that also we have done, that we rolled out last year into our cloud. But as you will see later, actually that's something we really want to contribute also to the community, and that's why we decided to open source that. That's called Xkeeper, and we're going to hear that in the next minutes from Paula. So Paula, maybe you want to take us through the...
Okay. So yeah, I'm going to start off talking about the use case from the weather company. And the weather company started with a simple mission to keep people safe and informed with the world's most accurate forecast. Please move to the next slide. So today the weather company has evolved into a decision solutions company with data at its core that produces 25 billion forecasts daily. The Weather Company History on Demand application provides access to a worldwide data set of past weather conditions via a web API. It provides global high-resolution grid with geospatial and temporal search. And it averages 600,000 requests per day and is typically used for machine learning and data analytics. So Our previous implementation of History on Demand had synchronous data access with several drawbacks. So firstly, it was expensive. It also had limited storage capacity. And we limited ourselves to land-only weather coverage and only a subset of the available weather properties. Clients were limited to small requests, and it was slow at retrieving large amounts of data, which is becoming increasingly important now for machine learning workflows. So we developed an asynchronous solution using a serverless approach, which Torsten already talked about. And this gives us a huge cost advantage since we don't need to pay for compute when there are no queries. Torsten already told you about SQL Query, which is serverless SQL powered by Spark, and it has a Hive metastore and geospatial capabilities. And for the rest of the talk, I'm going to focus on the data skipping aspects and how this dramatically boosts performance as well as lowering cost. So SQL Query has a very general data skipping capability, which avoids reading irrelevant objects based on data skipping indexes. And these contain aggregate metadata for each object. The indexes are created by users and they're stored alongside the data in IBM's cloud object storage. So we support multiple index types, including the standard min-max data skipping indexes, but also introducing others such as value list, Bloom filter, and geospatial index types. And our capability is extensible, so it's easy for us to add new index types. To our knowledge, we're the only framework which enables skipping for queries with user-defined functions. These UDFs could, for example, be functions from our geospatial library. Under the hood, we have an extensible way to map UDFs to index types, and this is picked up by Spark's Catalyst Optimizer. This goes beyond alternative approaches for data skipping, which are typically based only on min-max and sometimes Bloom filter, and don't support UDFs. Okay, so our code is an add-on library for Spark, which enables the modified query execution flow you see here. On the left is the typical Spark SQL query flow. There's a partition pruning step before reading the data from object storage. We introduced an additional pruning phase which consults object level metadata. This is done using the Catalyst Optimizer and the Session Extensions API. Okay, so here is a classic example of data skipping using a min-max index on the temperature column of a weather data set. For each object, we store the minimum and maximum values of that column. When evaluating a query looking for temperatures of over 40 degrees Celsius, Spark with our library will prune the list of relevant objects based on this metadata. In our example, the red objects are not relevant to the query and therefore don't need to be scanned. To build the index, we scan the temperature column once and store it in Parquet format. From then on, only the index needs to be accessed to make skipping decisions. Okay, so here is an example of a query looking for weather data in the Raleigh Research Triangle. In the optimizations, this query would need to scan the entire data set, even though all relevant data is in a small geospatial region. This is because Spark doesn't know anything about IBM's geospatial library functions, so it can't skip any of the data. To address this, we built min-max indexes on the lat and long columns, as you see on the right. To enable geospatial data skipping for queries like this, we mapped the ST contains UDF to min-max indexes on these columns. We also did this for the rest of the functions in the geospatial library. This graph shows this query running on a TWC weather data set containing 10 terabytes of Parquet data spanning 5 years. As I said before, without any optimization, these queries need to scan the entire data set and didn't even complete. So the next thing we tried was rewriting the queries by adding the region's bounding box as a hint to the Spark optimizer. And this exploits Parquet's built-in min-max indexes. This is the yellow curve you see here. So the yellow curve is already significantly optimized compared to the true baseline. Then we added data skipping and Hive Metastore support. This results in the blue curve. Averaging over all data points shown here, we get an order of magnitude speed up compared to the yellow curve, which, as I pointed out, was already optimized using Parquet's data skipping support. Okay, so this translated to order of magnitude performance improvements and cost reductions for the weather company. It also enabled moving to global instead of land-only weather coverage and supporting all 34 available weather properties. Users can now retrieve large amounts of historical weather data efficiently to train machine learning models. We achieved a 40 times speed up in cases that we tested. So I'm now excited to announce for the very first time the open sourcing of Xkeeper, our extensible data skipping library. Xkeeper works out of the box with Apache Spark, and it supports many open formats, Parquet, CSV, JSON, Arrow, and ORC, and also supports Hive tables. And out of the box, it supports min-max, value list, and Bloom filter index types. But you can define your own data skipping index types, use your own novel data structures, and apply to your own use cases. And the data can be domain specific, for example, geospatial data like I showed for the weather company use case, or could also be genomic data, astronomical data, and so on. You can enable data skipping for your own UDFs by mapping them to conditions over your data. Over your data skipping indexes. And you can achieve order of magnitude performance acceleration and beyond, just like I showed for the weather company use case. And this is even compared to formats with built-in data skipping like Parquet. So here's a snapshot of our site where you can access the code, full documentation for Xkeeper. So, please check this out and get involved. We welcome contributions, and 3 example areas of contribution are firstly, support for new index types. So new index types and UDFs can be added as plugins. We show how this is done by adding a regular expression index as a plugin in a separate repo. And the docs and code show you how you can roll your own. The library also supports, Apache Spark, as I mentioned, but support for additional engines can be added in future. And finally, we're data type agnostic and support all of Spark's built-in types, as I mentioned before, but we'd also like to support table formats such as Iceberg, Hoodie, and Delta. And in particular, we're starting to discuss this in the Iceberg community. And I'm sure you'll have additional ideas of how to contribute. So please feel free to reach out to us on Slack after the talk, and also using GitHub discussions on our repo. Okay, so thanks everyone for attending. And thanks to all the team, particularly to Guy Kazma for leading the Xkeeper open sourcing efforts.
Okay, thank you so much, Paul and Torsten. Torsten, if you could stop sharing your screen, we will go ahead and get started with the live Q&A. While I'm getting that going, I do see a couple questions from the in the chat. Nita Dembla wants to know, how is this different from Parquet's built-in indexes?
So the difference is that we support the metadata in a consolidated fashion. So with Parquet, the indexing information is stored in the Parquet footers. That means that in order to access that information, you go and access every single footer for every single object. So although you read less data, you still need to access all the objects. Whereas we take all of that information out and put it in a consolidated fashion as a separate Parquet data set. And that's for min-max. We also support additional index types that Parquet doesn't support, like value list, for example.
So the next question I have is from Mayank, and he wants to know how different is it from adaptive query execution as part of Spark 3.0? Do you want me to ask that again?
Adaptive query execution is a method of optimizing queries, but it's not data skipping per se. So what we're doing is we're enabling skipping over objects in their entirety in order to improve query performance. So it is a different method of optimizing queries and can be used in a complementary fashion. So
I believe it can be combined.
Improvements.
Yeah, I would also say that they should actually be combinable very nicely, actually. And
yeah.
Should add up, actually, the benefits.
Yes.
So Ryan Blue, one of our first technical speakers today, is asking, what is the difference between value list and Parquet's dictionary filtering?
So value list is a list of values, of unique values in the column of an object. And we store it in a consolidated fashion outside of Parquet data. So you would only need to access that in particular. It also works, aside from Parquet, it also works for all the other types like CSV, JSON, ORC, and so on. So I think, I hope that answers the question.
Okay, and let's do one more before we go ahead and do it. But can it index on in-memory cached Spark table?
So you can take data skipping indexes and cache them in memory in order to even further boost performance and avoid having to read the indexes from storage. So actually the performance graphs that we show don't do that. So you could get an additional speed up by caching data skipping indexes. And
I think that that's probably the last question we can take right now, but just a reminder that Torsten and Paula will be in their Slack channel after this to answer additional questions. There are a lot more questions there in the chat. I did pin a link to that Slack channel up at the top. And what I'd ask everyone to do now is go ahead and click on that Slido link over on the side of your screen to go ahead and fill out a quick survey of what you thought about this session. And I want to thank Torsten and Paula for their time today, and we'll see you over in Slack. Thanks so much.